All right, you should have downloaded 11.12, 11.2, or you should have written out a quick copy. It doesn't have to be beautiful, it just has to be enough so that you know what it is we're talking about. And we got basically one humongous chemistry idea to deal with, but it's actually fairly simple. If you follow along, you should be able to go, oh, I get it. That's what I'm hoping for here. Okay, so the first thing it says, let's say we have a sodium atom. Okay, so first thing I'm going to do is sketch a sodium atom. Now, again, I don't expect you to memorize what a sodium atom looks like. You just find one of your periodic tables. You're going to find that it says something like Na, and then it's got a 11 up here and a 23 down here. And again, that's all you need to know to draw it. So what I'm going to do is I'm going to draw it right now. I'm going to draw myself a sodium right there. I've got we remember that the 11 on top refers to protons. So 11 protons, I have 12 neutrons. Then I start filling my shells. Now remember, my periodic table shows that I can put 2 electrons on the first shell. It says that I'm done with the second shell when I put an 8 out there. Now, to scale, I should put these 8 way the heck out here. 1, 2, 3, 4, 5, 6, 7, 8. But I'm just going to go ahead and put them in close, like I'm supposed, like pretending they're the same thing. And then the last one, all the way out here on the edge, I had this 1 electron. It'll be like whizzing way the heck out here compared to the other ones, right? Because each one, remember, if I was a nucleus, my electrons would be whizzing through Reno, right? If I was living in incline. So that's a long ways with a lot of space there. This one guy's way the heck out there on the edge. So far, so good? All right. So that's my model. So sketch a model. It says, imagine this thing is spinning 20 times faster than the speed of sound. Now, I wasn't allowed to go to school yesterday. So what we're going to do is we're going to try something different. I'm going to try to do this with these high-tech, oh yeah, you waiting for it? High-tech, brand new technological devices. I don't know what the heck I'm doing here. Hold on. Where is the, oh, I thought I had it right here. It was right here a second ago. All right, let me see if I can find it. And select, there it is right there, select. Select, okay, so I'm gonna select this. Whee! Okay, so high tech, are you ready for high tech? So I'm gonna move it out here just a little bit. And it says rotate. Oh, no, rotating is not gonna work very fast. Okay, well, I'm gonna do it very fast. No, I'm not. Flip to vertical, boom. Flip again. Oh, no, it didn't let me do it again. Oh, bummer. Okay, so that's really not working. So, end of the day, this electron is way out here. See this guy here? It goes around one time every 0.0000000, I think I have enough 0 seconds. 1 seconds. In other words, this thing is whizzing around the outside approximately 1,000,000 times every second. So it's whizzing around the outside. It's got complete control of this zone out here. Okay? So if you were another atom and you're coming towards this thing, what are you going to hit? You're going to hit this 1 electron hanging out right here, right? You're going to slam into that. And so the only thing another atom ever runs into is this outside electron, right? So the thing it knows is there is an electron. So all chemical properties, every time one chemical atom slams into another atom, the only thing that's ever going to matter is that outermost electron, okay? So the chemical properties of sodium, this is sodium, remember, is decided by the outer shell of electrons. We call these valence electrons, okay? It's just a name, don't sweat it, okay? Now I'm going to do fluorine. Again, I don't expect you to memorize fluorine. Please don't memorize fluorine. That would be a humongous waste of time. So I'll make myself a pen here, go. Fluorine, again, you're going to look at it on the periodic table. I'm always going to give you a periodic table. You always will have it. In fact, if you go to chemistry classes all over America, you will always see fluorine here. Okay, so I have 9 protons. Oh, I'm writing with a mouse. Good luck with that. And I have 10 neutrons. And you should already know how to do this. If you don't, well, you should. And then I count across the periodic table, and I realize I've got 2 electrons allowed in the first shell. Boom. So I draw those in. The next shell all the way out here, I got 1, 2, 3, 4, 5, 6, 7. and I have a hole right here. Like there's an electron missing right here. I mean, I could fill it in, but it's not there. So there's my outer shell, right? So these electrons are whizzing around, but there's this one little gap right there. See it? Okay, so one little gap. So as this thing's spinning around, it's like it's 7/8 around it. It's completely surrounded by the shell. It's spinning so fast you can't get inside. And then there's one gap on the outside. It's one notch in the outside shell. Okay, so I've sketched it. Good, that's sketching fluorine. Okay, so you're back at the first page already. You're back at 11.2 already. So it says, second, imagine the whirling around at speed 20 times as fast as the speed of sound. Can't do it. Watch the demo again. I don't have the equipment with me. I do apologize. But if you imagine, it's a complete sphere, except there's one pie piece missing out of it. It's like a Pac-Man. It looks something like, if I want to do it, it looks something like this. It's got this gap. And every place else there's an electron. There's one big hole right in the middle there, that outer shell where, you know, something can run into it a little differently, but everything else is going to bounce off that outer shell. Okay. So if you're another atom, let's say there's sodium coming along, and you run into this, there's sodium. If you run into the fluorine, what are you going to run into? The outside's going to run into the outside here, right? Okay. So the only thing that can matter for fluorine also is the same thing. In fact, for all atoms, the only thing that's ever going to matter is your outermost shell of electrons, because that's what you're going to run into. With me so far? Okay, now I'm going to shrink this down while you go to the second page. Look, we're already done with one of the 2 pages we're going to do today. What? Yeah, I promised. We're going to be there. We're getting there. Okay, so shrinking down that atom. I shrink down this one too. Here we go. Whoop. Shrinking down this one. Okay. Oh, I smashed it. I wasn't supposed to smash it. I apologize. Okay. No. So I got these 2 atoms right here. Sodium, fluoride. With me so far? All right, so next thing on the list. Let's say you are a new atom. You're a neon atom. Okay, so neon, if I look at my periodic table, says, and by the way, listen, I'm getting out neon. I'm getting out the periodic table, right? Because I don't know what neon is. According to the chart, neon is 1020, right? So I'm going to draw this sucker up. So I don't expect you to memorize this. I do not want you to memorize how many protons and neutrons. No, well, I shouldn't say nobody does, but very few people do. There are some people that have some time on their hands. We don't care. Okay, so then I count across the first row. I don't remember how many electrons go to the first shell. Well, if I look, it says helium is happy with 2, right? So I got 2, boom, in the outermost, in that first shell. And then it says I can put 8 more, but when I get to 10, I'm happy. So I got 10 in the second shell, boom. 1, 2, 3, 4, 5, 6, 7, 8. Now these things are whizzing around again. Whizzing around, going full speed. Can't touch this. So now here's the problem. Is there a way for an electron to get in out here? There's no place in, right? There's no holes in this, right? So when this thing hits something that has electrons on the outside, what does it do? Nothing. There's no holes. This thing just bounces off. It's going to stay bouncing off, okay? So you're still going to hit the outer shell of electrons. The outer shells of neon, the chemical properties of neon are decided by the outer shells of electrons, like all the other atoms. We can call these valence electrons, okay? So what have I said so far? Not much interesting, right? When we do the shells, we know how to do the shells now, because we've learned that. We know the outermost shell is what you're going to run into first, right? And what we may not have known is that the electrons are traveling so fast you can't get past them. You're going to run into it. You can't possibly move fast enough without running into the outer shell electrons. So the outer shell electrons are going to determine what's going on at all times. Okay? So I'm done with the front part of 11.3. We go to the back part of 11.3. Here we go. Now, what does this mean? Okay. First of all, let's talk about neon. Neon has no holes in it, right? So as it's spinning around, when things run into it, what happens? Answer, nothing. Neon is boring. It's a noble gas. It reacts with nothing. It can't take electrons. It can't give away electrons. It has a full shell inside our cell. It's happy. And in fact, since all the right-hand rows, helium, neon, argon, krypton, xenon, radon, all have full shells. Every single one of them is is chemically inert. They do nothing. They're bored. Useless to us. Okay? So I'm going to quickly get rid of that. Does that make sense? So because they have a full shell on the outside, they do nothing. And we call them noble gases. And all the noble gases react with nothing. You put them in a room that's on fire. You put them with the most nasty chemical on the planet. Remember that sodium blowing up the lake? Sodium and neon does nothing. Sodium and helium, nothing. Boring. All right. Let's do that. Chopping this out of here. Boom. I'm going to cut and paste it out of here. Cut. I thought I could cut it. Oh, there's cut right there. Boom. Okay, so now I have my sodium, my fluoride. Now things are going to get really much more interesting. Okay? Let's talk, shall we? What does sodium do? Well, imagine for a moment you're a crazy kid and you've got a big old stick with a rock on the end of it. And it's like a 10-foot long, skinny popsicle stick. You're not even really holding on. It's like a rubber band almost. And you go spinning in a circle like a crazy person. What do you hit? What hits first? The stick with the rock in it. What breaks first? The electron. This electron here, remember, we just said is going really, really fast. Whoops, I didn't draw that. Do that right. This is going really, really fast. This way. If it runs into something, anything, it's going to go off. And poor sodium's going to be left with this lost an electron. It had one, but it's gone. Okay? So what does sodium do? Sodium, because it has one electron on the outermost shell, likes to lose its one electron, which gives it full shells underneath and makes it act like neon we ran into earlier. The full shells mean it can't react with anything anymore. So once it loses this crazy electron, it's got way the heck out here, it becomes stable. It becomes chemically inert. Okay? So when you throw sodium in a lake, sodium has water in it. Water loves to steal electrons. Okay? What happens? That electron gets stolen by the water. Boom! Mass explosion. It really wants to do that. But right afterwards, what is sodium doing in a lake? It's sitting there. It's bored. Now, one other thing to remember. It just lost an electron. Now, we talked about electrons having negative charges before, right? This has got a negative charge. So if I lose one negative charge, what do I become? This is a little tricky. I have 11 positives and 11 negatives. But if I lose one negative, I have now 11 positives and only 10 negatives. So I become +1. So the charge in the sodium becomes +1, right? Okay. Now, so what does sodium do? Again, it wants to get rid of that one electron hanging on its outermost shell, and that's what causes it to become stable and stop blowing up stuff. Once it has the one, if it still has that one electron, it's crazy talk time. The moment it loses it, much more mellow situation. It's relaxed. It's sodium. It's the sodium that's in your salt, right? When you put salt in your mouth, it doesn't explode. We call it sodium chloride. Why doesn't it explode? Because it's already lost the electron. If it still had the electron, putting it in your mouth would be a very, very bad idea. See previous video if you're in doubt of what I mean by that. Now I'm going to have to stop this video because I'm going to run out of time, and I still want to discuss fluorine. So here's what we're going to do. I'm going to stop this video. You go ahead and start up the next one.